them briefly, and then you'll have time to go critically look at the materials and also practice. There are a few assignments and exercises that you need to do to understand part of this. So today we are going to discuss one of the most important components in an RF transmitter, which is called the power amplifier. So as you may know, this is one of the interesting component in transmission, and it is normally the last stage in the block diagram. So if you look at any wireless system, whether it is a mobile phone, Wi-Fi router, whether it is a radar transmitter or a satellite communication link, the final stage that actually pushes energy into the antenna is the power amplifier. So, and the power amplifier is one of the complex and exciting device, but also challenging to design. And this is where now the engineering problem sits. This is where you become RF engineers when you design some of these powerful systems like the power amplifier. So why is this very important? Is because it forces us to balance some competing engineering requirements. For example, you have what we call efficiency. You want to achieve efficiency, but you also want linearity so that you don't have much distortions, and you also want to minimize heat dissipations. Remember, there could be some heat generated, especially when you don't have good matching devices. And the goal is to ensure that you balance these parameters to ensure that your device works perfectly well. So in this lecture, we'll look at how power amplifiers work. We shall also look at the structure of the power amplifier, especially the block diagrams that you later look at in groups, and also design some of these ones. And also we shall evaluate the performance. We shall look at the performance of the power amplifier and how to achieve the desired performance. And also we shall look at different types, so what we call the classes of power amplifier. Some of you are good at electronics or have done electronic course very well, so you know how to design amplifiers, and you also know the classes of amplifiers as well. So when we talk about RF, what do we mean by RF power amplifier? So the radio frequency power amplifier is an electronic circuit device. Yes?
Yes.
You're admitting people, or? Yeah, there's someone who was asking. Is there a problem? Okay, so let's proceed. We said the power amplifier is one of the powerful circuits that is designed to increase the power level of a radio frequency signal. And this is because when you do the transmission, sometimes we lose the power and our signal becomes weak. Therefore, we need to boost it and do amplification. So before we transmit it into the antenna, it needs to be boosted to a level that you can recover the signal. So the power amplifiers in RF systems are the final active stage, like I said, and in the transmitter chain. And the purpose of these power amplifiers is to deliver sufficient signal power to the antenna while maintaining acceptable signal fidelity and also efficiency. Now, when you talk about signal fidelity, I don't know whether you've come across that term, but signal fidelity is when the transmitted signal is able to be reproduced, okay, at the end of the transmission without any distortion or alteration. That is signal fidelity, and we always strive to achieve this one. Then you also have what you call the efficiency, and you also need stability within the signal so that you don't lose any any quality of your signal as it is transmitted and received. Okay, so the architecture for the transmitter, it has different blocks. First and foremost, we have the RF input, and this is normally the one that receives the modulated signal. And then you do what you call the matching, the input matching, whereby you ensure that the maximum power that is received from the modulated signal is the one that is being transferred to the next stage. And this other next stage is what you call the active device, or what you call the transistor. So the transistor, its function is to convert the input, or what you call the supply DC power, into what you call the RF power to be transmitted. So it converts from the DC supply into the RF supply to be transmitted. And then the other side, you have what you call the output matching. At this time, you know what matching means. And especially this matching stage is to ensure that there is no refraction, or the signal is not reflected back to the source to cause heating and also the standing wave ratios. And then finally, you deliver your power into what we call the antenna. Okay, that will be the final stage. We shall look at this block diagram, and you will also design one. And next week, the next coming weeks, we shall also do practicals on how some of these are designed and simulated as well. So basically, when you look at applications of RF power amplifier, they are mob in wireless communication systems, whereby you have mobile communication networks, okay, the GSM networks, the 5G, you have the Wi-Fi transmitters, you have the satellite communication, you have the radar systems, basically, and mostly the broadcasting systems, they all use what you call the power amplifiers. So understanding this device, how to design it, and how to optimize the power is very, very essential for RF engineers. I hear some feedback. I don't know who is not muted and has some sound on.
Mr. Tusime is unmuted. Let him mute.
Because I see some I hear feedback, and it is maybe to see me. Have you muted? Yes, I think he's now muted. Yeah, there was some feedback. Okay, so let's now proceed and look at the performance metrics. And these are very, very key. Yes, the performance metrics, like I said, there are a number of competing metrics or parameters that you need to balance when you're designing your RF power amplifier. First and foremost, there is what you call the output power, and this has to be boosted to be able to reproduce the signal, the desired signal that is delivered to the load. Okay, and you have what you call the efficiency. And when you talk about the efficiency, this is the ratio of what is at the output to what was sent to the input. And preferably, you need it to be at least 1 or 100% efficient. So efficiency tells us how effectively the amplifier converts your DC power at the source into what you call the RF power for transmission. And any power that does not become RF signal, so becomes heat. And definitely you know what heat means, and you always want to avoid this one, the heating. And we also have the linearity. The linearity, this is extremely important in modern communication systems. And this is where the amplifier needs not to distort your signal that is sent. So it creates what you call interference in adjacent channels if it is not linear at all. That means if we are choosing the class of the amplifier, we need to ensure that the linearity aspect of it is looked at critically. Otherwise, you have some interferences, and also you might interfere with the neighboring channels, no frequency spectrum, how it works, or adjacent channel power, and also you have errors, okay, in your transmitted signal. Then we have what you call the gain and the stability. When you talk about the gain for any amplifier, you know, the amplifier, you get the input and then boost it. So what you do, you multiply the input with the gain. If, for example, you transmit 1 watt and at the output you need 10 watts, then the gain is 10. So you get 10 multiplied by 1 and you get the 10 watts at the output. So that is the gain. What you need to boost, how much do you need to boost your signal? That is the gain. And later we shall see how to calculate, and you'll be able to calculate the gain, both, yes, a direct method and also in decibels. Gain is normally calculated in decibels. And finally, the stability, a poorly designed RF amplifier can oscillate and effectively becomes what you call an intended RF transmitter. So it might give you instabilities, and eventually you get wrong operating conditions. And this is very, very unfortunate. You need to balance the stability as you design your RF amplifier so that it behaves correctly under all operating conditions. In case there is some noise, there is some external factors, then they need to be filtered out, factored out, so that your signal still remains clean. Okay, and these are very, very important parameters, and you need to pay attention to them, especially when you're designing the RF power amplifier. So let's look at the structure, the power amplifier, and this is what we call the internal working or the internal architecture, your RF power amplifier. So to understand how power amplifier works, we need to look at its internal structure. Okay, so at the heart of the amplifier is what you call the active device. And this is very core. Typically, this active device is what you call the transistor. You know, we have passive devices, but here we are interested in this active device, which is a transistor. And this is the one that converts the DC supply power at the source into what you call amplified RF power that is transmitted into the antenna. So this transistor alone is not enough. We need additional circuitry around it. And some of these circuitry that we need include what you call the input or the impedance matching networks. And in these networks, we have what you call the input matching and also the output matching of these ones. When we talk about the input matching, here we need to ensure maximum power transfer. So the input matching ensures the power that is received from the modulator or the modulated signal is good enough to be transferred, okay, to the next stage. And then we have what you call the output matching. And the output matching, this is where you ensure there is efficient transfer of power from the transistor to the load. So the transistor is now in between when it converts the DC power supply into the RF power supply. Now this is transferred into the load. And this matching network ensures that the powers balance and there is no reflection or there is no heat generated due to imbalance of power. Remember, power that is not matching, then it will be reflected back and it becomes heat, and there is a problem. So finally, we use RF biasing and also stability techniques. So when we say biasing, we want to ensure that our transistor is operating well within its region operation. Later, you'll learn about the cutoff operations, and also in choosing the amplifier classes, you have to ensure this biasing does not affect the operation of your amplifier. I already explained the stability. So together, these elements from the functional structure of a practical RF power amplifier becomes very, very important, and for each is a stage that you need to design, look at critically when you're doing your design. So we have what we call these active devices, the different types. And of course, you know some of these ones. And when we talk about the transistor, you know transistor types. And you take your time to read about this. But we have what we call the bipolar junction transistor. Okay, and this is very widely used, especially in amplifiers that operate at low frequencies. Okay, and this, yeah. So, however, they can suffer from what we call thermal instability. These can generate a lot of heat, BJTs. So, the advanced is what we call the MOSFET. And this provides easy integration, and they are also widely used in medium power RF application efficiency. So, these are middle range category of the amplifier. Not extremely low frequencies, but at medium frequencies, you can use these MOSFETs. And then for higher frequencies, we have these LD MOS transistors that you can better look at. And also we have what we call the GAS, gallium arsenide, and also gallium nitride technologies. And these are advanced technologies, especially they use field effect transistors, the FETs. The other one uses the MOS. The other one is, so this one uses the FET. And these are for high frequencies, and they offer what you call high power density and also efficiency, good efficiency for the advanced applications. So because of these properties, GAN is now widely used in radar systems. Last week, we looked at radar systems and what is most applicable at radar, because radars use high frequencies, is this GAN type of active transistor. Okay, but in the notes, you'll learn more about this, and you can also dig deeper to understand the working principles of these ones. Then let's look at the classes of amplifiers. Okay, so power amplifiers are categorized based on something called the conduction angle. Okay, and this conduction angle, it is like the full cycle of the transistor. So if you have like a sine wave, a cosine wave, whatever wave you have, so that full cycle, when it is on, that is the conduction angle. And these different transistors, they are separated by what you call the conduction angle. That's how you can differentiate them. How much your whatever your device is on, for the entire cycle. So when you look at the class A, the class A amplifier, it conducts for the entire cycle. And this, the conduction angle is 360 degrees. And this is very good because it remains linear. So it is very linear, but low efficiency because when it is on, it is consuming a lot of power because it remains on. Even when RF signal is not there, it is still consuming a lot of power. So it is suitable for high fidelity applications. This fidelity, I explained fidelity, what it means that you need at the end of the day, your signal to be reproduced exactly as it was sent. So for this, then you use what you call class A amplifiers. Then in class B amplifiers, this one, instead of conducting the full 360 degrees or all the time on, then it is off for some time. So this, the conduction angle is 180 degrees. So it is on for 180 degrees and also off at 180 degrees, so exactly half. Okay, so it offers high efficiency, but it introduces what you call crossover distortions, and this affects what you call signal quality, especially at crossing, at zero crossing points. So it offers what you call an improved efficiency, but introduces distortion at the switching point. Yeah, so you can see. Then the better one that is normally used in modern in communication, especially it is called class AB amplifier. So this class AB combines the advantages of class A and also the advantages of class B, minimizing the disadvantages in both. Okay, so it combines class A and class B and it conducts between 180 degrees to 360 degrees. So it is in between. Okay, it can go up to the 360 and also come to 180. So it balances linearity and efficiency. Very effective. So this offers a compromise between efficiency and linearity, and this is why it is the most common class used in communication transmitters. So if you go for any interview and they ask you, they normally ask some of these. Which type of amplifier is mostly used in transmission systems or whatever? So you need to mention class A, B, and also give the reasons why you feel this is very, very important. And you have what we call class C, finally class C, and also the other switching amplifiers. So the class C offers what we call very high efficiency, but are highly non-linear. Okay, they are highly non-linear. And this one conducts at less than 180 degrees for high efficiency, but the linearity is affected. And it also offers what you call the switching. So this is where you want to switch to be send the signal in bits on, off, on, off, on, off. And here you're minimizing what you call the power consumption and optimization. You can be admitting those people that come late so that they don't miss out. We are almost ending by there because you need to go into your groups and do some work. And while discussing transistors, you need to understand the biasing effect because for each class of the transistor, there is a way it is being biased. For example, in class A, the bias, it is biased in the middle of its operating region. For class B, it is biased at the cutoff point. Okay, so you need to understand some of these biasing techniques, and you've done transistors. So when I talk about biasing a transistor, you understand. So let's look at the efficiency. So efficiency, like I said, it is the ratio of the output, RF output power to now the DC power that is consumed. And this is expressed as a percentage in the power amplifier design. So they will say this one is 80% efficient. or 50% efficient. So the closer it is to 100, the better, because that means the output power is closer to the input power and the efficiency is good. So efficiency, for example, if an amplifier consumes 100% watts of DC power, but only delivers 50 watts of RF power, then the efficiency is 50%. Because it was 100, now it is at 50, then the balance, when you do the ratio, you get half, and this half is 50%. So that means the efficiency is 50%. And the remaining, if the efficiency is 50%, it means the remaining 50% is converted into heat, because it is not consumed. It is converted into heat, because they might ask you why efficiency is very important. It's important because you want to minimize the heating effect. You want all the power that is delivered is entirely consumed or converted. So in real systems, we also consider what we call the PAE, or what you call the power added efficiency. And this, you consider, it accounts for the input drive power as well. So there is what you call the input drive power that is provided, that provides the realistic measure of amplifier performance in communication systems. So you will also see in the notes I provided, so they are the formula for computing these, the efficiency, the PAE, and also examples. So you look at them critically and also understand and practice. So efficiency becomes particularly important in systems like mobile phones or base stations, where energy consumption and thermal management are major design concerns. Okay, this is very, very important. Okay, where you don't need to generate. Imagine now your mobile phone is hitting all the time. There are also mobile phones that are hitting all the time, and it means the efficiency is not good. The power is not fully utilized, and the balance is converted into heat. And your phone or your mobile phone is always heating. Okay, so you need to find a way of balancing this. So efficiency becomes particularly important. Okay, and it is a design parameter that you need to look at, especially to avoid what you call saturation. Okay, in transistors, operating in a saturation region. Then let's look at the gain, because when you talk about amplifier, without talking about gain, so there's nothing. Because without a gain, then you have not amplified anything. Maybe if the gain is 1, sometimes you find the gain is 1. Especially if there is a bridging network that you want to build, you want to transfer exactly what you receive to exactly the output, but you need a bridge in between. You can design an amplifier that has a gain of 1. Okay, but in most cases, gain is more than 1. So gain tells us how much the amplifier increases signal power. Okay, how much the amplifier increases signal power. And in linear terms, gain is simply the ratio of output power to input power. The ratio of the output power to input power. And this one, you also calculate it in decibels as well. And there's a formula that we use, especially the 10 log something. You'll find it in the notes, and you'll be able to calculate the gain using that decibels formula. So the formula for power gain is 10 times the logarithm of the power ratio. Yeah, you'll find that. So understanding this gain is very, very important, because it tells us how much drive power the amplifier requires from the earlier stages. Yeah, remember we have different stages. And for each stage, if the signal is weak, then you need to boost it. And this gain is functions well in improving or boost the power. So, however, gain is not unlimited, yes. So as we push the amplifier harder, you need to do the balancing. That's why you called engineers. So as we push the amplifier harder, it eventually reaches a point where the gain compresses. So it is not infinity. It reaches a time where it can compress, and this is called the 1 dp compression point, and it marks the onset of nonlinear distortions. So you can have a gain that will also distort. So we need to also to balance it somehow. Okay, so let's look at impedance matching. I think for each and every lecture we have talked about this, and by this time you understand what impedance matching means. And you also have, different techniques of how you do the matching, and you've done some computations. Okay, and in RF systems, you need to talk about matching. So impedance matching is absolutely essential, and you can't avoid it. So maximum power transfer occurs when the load impedance is the complex conjugate of the source impedance. And let me see if I can, but let's see if I can get a pen and I show you. You need that complex conjugate. Let me see where is the pointer. I have the pen. Yeah, so for example, I'll show you some example how you do that. If you have the source impedance, the source, okay, I can say this is the source. I'll give you a technique how you can determine. And you have your resistive network plus your reactive. And you can have X here, the X value. So if this is the source impedance, then the load impedance must be the complex conjugate. The load has to be the complex conjugate of that. And this is how they write it. S star. Okay. And this is given by, once you have that, then you can just change the other one into, you take the conjugate of the other one and it becomes this one. This is how you do your matching. And this is very, very important. Okay. And when you do this, it means eventually this negative and the reactive part will cancel. And then you find you have the resistive part that is the same. And that matching will be good. Okay, that's how you will find it in the notes as well, how you do the matching. Okay, so in most RF systems, we standardize on 50 ohms. You'll find they talk about the matching of 50 or the impedance of 50, the impedance of the load. They normally say it is 50 ohms. And you've seen it. It is a standard. It is de facto standard. And you even see the reason why they use 50 ohms as the reference impedance. And however, the intrinsic impedance of the transistor is usually not 50 ohms. So that is where you need now to do the matching. Therefore, we use matching networks to transform impedance between the source device and the load. And these networks can be implemented using several techniques like we looked at, okay, including the transformation technique that we looked at in the previous lectures. So without proper matching, a large portion of the signal power would simply reflect back towards the source. And you know what reflection means? It causes heat, standing waves, pressures, and the rest, and also distortions and the signal loss. Okay. And finally, let's look at thermal considerations. Now, if the matching is not good enough, then there'll be some heat. So in your design, you need to properly plan for the heat dissipation. So in case of some heat, what do you do? So normally here you have the techniques, you have like the heat sink, you have the cooling techniques. You sometimes cool using air. There is air cooling. There is also liquid cooling at high frequencies. So remember that any power that is not converted into RF output becomes what you call heat inside the transistor. And if this heat is not properly managed, the device temperature rises, and which can degrade performance, and eventually it causes failure. So engineers therefore use several cooling techniques, and these include the heat sinks, the forced air cooling, and sometimes liquid cooling in high power systems. Yeah, I mentioned this one. So another important parameter is what you call thermal resistance. And this is very, very important. It describes how easily heat flows from the transistor junction to the surrounding environment. And this proper thermal design is essential for ensuring long-term reliability. Okay? And it is also very critical for maintaining device reliability and also performance. Yes. Okay, so the practical consideration, also I talked about this one, practical design considerations. What do you consider? Linearity, we said it is very, very essential and you need to understand it. So in real world amplifier design, it involves several practical constraints beyond theoretical calculations. Yeah. And for modern communication systems, linearity is extremely important. Okay? Extremely important. And at the same time, we still want high efficiency. So you can see the balance. You need it to be linear, but you also want the high efficiency to minimize power consumption and also heat generation. So we also need to ensure stability. I talked about it, and so that the amplifier does not oscillate under different load conditions. Yeah, you need to do what you call stress testing. Okay, you test your amplifier in different conditions to ensure that it remains stable, all conditions, and it works well. And finally, we must suppress what you call unwanted harmonic signals using filters. So this is where you have the low pass filters and also, yeah, to comply with spectral emission regulations, because sometimes there are unwanted signals or there is some noise. So you need to do the filtering so that you don't introduce other harmonics into your signal that will cause signal distortions. And so in practice, PA, what we call the power amplifier design, becomes a careful balancing act between many competing stars. Yes. And yes, I guess we stop here for now, and then you have an hour to also go through the lecture materials. I will also send you the slides and also do some exercises in your groups, do some group reflections, and also submit to me, because yeah, I told you need every week to do the reflection, the group reflection, to see how your learning curve is, the materials you read, how you're understanding them, and also the techniques you're putting forward to understand even better the things you're not understanding. Okay, and for each module, there is always a practice exam question that comes with, and also the assignment. Please take these ones like seriously, okay, and practice them. I don't want you at the end to be like, oh, we need practice exam, or we need to tell us how you're going to set exams. No, these ones are already embedded and included. And eventually, I know you're going to enjoy this course as long as you understand the basics. There's nothing hard. and also those calculations, the formulas, understand them. And even during the exam time, I will have the formula sheet for you. Don't cram the formulas, just understand how they work. Okay, so that's it, unless there's a question or anything. And